Okay, so welcome to week 4. It should be open on your Moodle accounts. Let's see. So we're going to start with essentials. Chapter 4 starts on page 99, the information. And this is all about the nervous system and the basics of how it works. Okay, so the nervous system mainly utilizes what's called neurotransmitters, and these are just chemicals that are able to cross over a synapse, and the synapse is just a break in the gap between the two nerves that are coming, the neurons. Page 99. Okay. And remember that the nervous system is one of the main regulatory systems of the body. And it's regulating the environment, trying to maintain homeostasis at all times. Okay, so a synapse can also be between a neuron and a muscle cell if it's at the end and it's going to give the message of instructions from the brain the muscle's supposed to work or not work. Or a gland sometimes. Hormones do this too, but occasionally the nerve will also be involved. Okay. So if the hormone is the same thing as the chemical, then it depends on which what system's using it, if it's called a chemical, a neurotransmitter, or a hormone. If it's the endocrine system using it, it'll be called a hormone. If the nervous system is using the same chemical, it's now called a neurotransmitter. All right, so we also have feedback loops, of course, part of the regulation of these sending and stop sending the messages. The function of the nervous system is to sense, interpret, and act. Page 100. So sensing is collecting data from the environment. Interpreting is figuring out what that means and if we need to do anything about it. And then acting is telling the body whatever instructions it needs to respond the proper way. Remember the air conditioning example, okay? The divisions of the nervous system, central and peripheral nervous systems. The central nervous system, or CNS, is composed of the brain, the spinal cord, and the coverings of all of this, meninges and so forth. The peripheral nervous system is having to do with all the things attached to the CNS, spinal nerves, and all the other subdivisions of the nervous system. So only the central nervous system is without any other subdivisions. Okay? The other little buddy nervous systems are part of the PNS, always, okay? So that includes your somatic and autonomic nervous system, which includes our fight or flight response, which is sympathetic, ramp up everything, and the parasympathetic, which is what we're usually fighting to activate, which is calm down, relax, everything is okay, be peaceful, digest the food again, heal, all that stuff. Okay, so if you are trying to go to sleep and you hear a boom outside your window, which nervous system is activated? Sympathetic. Yes, the other S. Sympathetic. You're aroused, right? What was that? Do I need to do anything? Do I I have to grab a weapon, or do I need to get my kids, or, any of those things. Once you're sure it was a squirrel that fell on top of whatever, then you can go back, come down and go to sleep. If it's gunshots, then you're going to continue the arousal process, okay? So that's the whole point of the nervous system. So we do need it to work properly. And when it goes haywire, then we get aroused too much over minuscule, non-important, non-threatening things. Same thing with the other systems in the body that can happen with. All right, enteric nervous system. This ENS for short, this is part of your autonomic nervous system, and it's part of your parasympathetic, and it is what is involved with your digestion, whether it's going to be working or not. So it's nicknamed the little brain of your gut. It's within mostly in our intestines, and our vagus nerve does play a role in the functioning of this system. Yeah, I'm sorry. And any system can have breakdowns and have disorder happening. So a lot of the mind-body connection happens through our autonomic nervous system, and that's important because if we're trying to save our life, then we need the energy for that purpose, and we take it from non-essentials. It's essential sometimes. Digesting food is essential. Creating urine is essential. But not when we're trying to crawl up a tree to get away from the dog that's trying to bite us, right? That moment, we don't care about breaking down the morning donut. We just want all the energy to push our body up as high as possible, as quickly as possible. So it checks in. I'm stealing your energy. And it doesn't need a fight to happen. It doesn't need the system to go, no, I'm almost done digesting this. It just needs to be able to take it. It can say, override, I am now the boss. You can have that hat back in a second. Okay? All right. Now we'll talk about kind of the structure of the nervous system. So we can kind of see the flow, the overall sense of the different parts, and all the nerves are kind of grouped together. And then there's a nice little tree there breaking down the subdivisions of each system. So the central nervous system has the largest organ in it, the brain, but the peripheral has the most different parts. Okay. Structure of the system. So the nerve cell is called a neuron. That's what they are. And each cell, there's different types. We have afferent, which are sensory neurons. They go towards the brain or CNS. They're carrying sensory information that it has received from the environment, sending it to the brain so the brain can interpret it and tell us if we need to do anything. It's kind of like you go to the doctor, you get a scan. You have to send it to the doctor, he can read it, and then he will have notes for the nurses or whoever. Do we need to reschedule? Do we need to come back today, tomorrow, 6-month checkup? Oh, it's nothing. Or, oh my gosh, this could burst and kill them in a second, so we need to go to surgery. Whatever the instructions are, then the CNS returns with the afferent information or effector. What do we need to do with this information? So, afferent is same thing as sensory. Efferent is motor. It's going to go towards the body parts to tell it with its instructions. Okay, axons. Axons are projections that are branches that come out and allow communication among a lot of different neurons. Be familiar with axons. Dendrites look like little hairs. Axons are a little bit longer. Okay, there's some dendrites here off the end of that neuron right there. And axons, branches of axons can be called collaterals, as this one shows. It's branching off. Okay. So motor impulses are called what type of neurons? Effector. Good. And sensory is afferent. Page 102. Neuroglia. This means nerve glue. This gives the support and protection. It allows for nutrient exchange to happen along the pathway between the blood-brain barrier situation in the spinal cord. CSF, cerebrospinal fluid, lives within the spinal column. Talk about spinal taps and things of that nature. That's when we're going into that region to try to numb it or whatever. Because we only know we're in pain if the brain gets the signal, right? So if we can block it and we don't know that it's hurting, then we can stay still for the surgery. So the protective covering or fatty sheath is called myelin sheath. They're also known as Schwann cells, that outside layer that's around the myelin sheath. But altogether, it's called a neurolema. This is still on 102. And they're able to help regenerate an axon if it gets injured. So it has to have that insulation, that protection. When we have nervous system disorders, usually it's involving the breakdown of this protective sheath of the myelin, like MS, for example. It's attacking the myelin on the nerves, and so therefore they have a lot of pain because it's basically, it's winter all the time, and it keeps throwing away the jackets. It keeps burning them up, and so it's hypersensitive. Okay, so nerve repair and regeneration. When a cell gets damaged, the neuron usually dies. In the central nervous system, this is always true. In the PNS, there is a possibility of repair because of the myelin and the Schwann cells. So that's good. But that's why we have paralysis when we have injury to the spine, because that's where the CNS is located. And you damage it, that's it. So that's the difference too between the two separate sections of the nervous system. All right, nerve cell function. Membrane potential on 103 briefly. So sodium and potassium both play a key role, and there's a couple others. We usually call those electrolytes. That's why they're important. They play a key role in deciding what action that the nerve cell can take or not. So there'll be a stimulus. It depends on the charge, negative or positive. If it's positive on the membrane of the cell, and the inside is negative, the outside is positive, then it has membrane potential, and it is called a polarized cell when they have opposite charges. So if it is stimulated with pressure, then there'll be a brief change. You'll be able to detect it, and it'll be able to react. If it is not stimulated, then it has resting potential. It's resting, it has the potential to do work, basically. Okay. Whenever it gets stimulated, there will be a change in the charge. It will change, kind of get neutralized, and then it will be called depolarized. It flips. And when that flips, it's called active potential. It gets sent off. That's a nerve impulse. Make an impulse buy. It happens very quickly. That's where that comes from. You don't have to think about it, right? Breathe, heartbeat, all that stuff is just happening. The brain's constantly regulating. Is it still working? Yes. If something stops, then the brain says, okay, we need to steal energy from this, and we need to focus on finding out what's going on. Okay, so a little bit more on nerve impulses. Here we go. So resting neuron, polarized, not stimulated, that's resting potential. If it gets stimulated, that change makes it depolarized. So we have a little figure 4-5, shows you a little bit of what that can look like. Sodium helps the nerve go faster and conduct its message or impulses faster. So there's potential, and with the sodium there, it's going to receive it quicker and send on its impulse. So it's kind of like a wave, lightning fast wave. That's why they refer to it like electricity. Shoo. When it's working right. Okay, along this pathway, there are gaps that you can see along between each node. The gap is the synapse, and it's called node of Reindeer. That's gaps in that myelin sheath or insulation. They name every little thing. So that's called the node of Reindeer. Some guy named Reindeer discovered this little gaps. Stick my flag on it. Okay, and so it happens at regular intervals, and it jumps along like a little white stone skipping across, sending it down. Now, because sodium helps this to happen faster, that's called saltatory conduction. Sodium, salt. Okay, at least that one's easy to connect, right? Okay, so people say everything's better with salt. Nerves are better with salt, as long as they're not hyperactive. Okay, so now let's talk a little bit more about the synapse. So the space between the neurons is the synapse. It's got to cross that. The chemical signals that it needs to cross the gap is the neurotransmitters. If you have the correct one, it will work and go through. Kind of like the cell has a little lock and key for their connections with the compounds. So we have over 30 neurotransmitters that have been found and tagged that we know regulate body activities, and they're related to the hormone chemicals too. Okay, there's probably some more that they'll find later, just like there's other parts of life in the world that we don't know about. We just haven't named it and found it yet. Okay, so they're always studying them and finding more. But neurotransmitters help push this nerve impulse across the gap to the next cell so it can continue on. So the space in the synapse is called the synaptic cleft. Think of a cliff, the edge of it. Okay. And the neurotransmitters hold I'll say vessels, but it's vesicles. But just think of them as vessels holding the neurotransmitter. And they release it in response to the nerve impulse. to allow it to keep going. So there's a lot of cooperation happening between all these little parts. And so the neurotransmitter is what causes that action potential to continue to cross over the synaptic clefts and continue transmitting this information. So saltatory is going to speed it up. Neurotransmitters that slow down this message impulse being sent are called inhibitory. It's inhibiting, it's slowing it down. And we use those in medicine. They take it from the body and they try to supersize it and make a pill to sell you. Like you may have heard of gabapentin. It's a calming down the nervous system pill. Well, the neurotransmitter is called GABA. They made a pill based off of GABA, which is a nerve calming, inhibitory neurotransmitter. All right. Role of the neurotransmitters 106. I gotta update my slide. 50. They found 50 neurotransmitters so far. But anyway, they know that they can be released into the bloodstream, and of course, depending on which system's using them, they have a different name. There are 3 categories: amino acids, amine, and peptids. Amino acids, you've probably heard of the most. Peptids, probably second, I would think. But they all have different characteristics of all associated with them. Peptids, for example, will have a longer term effect than the other 2. Just little differences like that. All right, body chemistry and behavior of pain. So we have pleasure sensory information, we have pain sensory information, and we have survival mood. There's different neurotransmitters that will be released depending on what's going on. Our behavior is affected by that. When you are in excruciating pain, how does your behavior change? Just on the average. Yes. Easily irritated, right? You have your patience goes, get snappy, right? I don't want loud noises, children. Shh, right now. Mommy has a migraine. Or something like that. What else? But you get the idea. So our behavior is very linked to the modulation of these things. So when we have something that we know makes us happy, pleasure neurotransmitters get released when we hear, see, smell this thing again. Because, ooh, I've experienced it. Good things happened. So I already feel happier because I'm aware that it's nearby and I have access to it. The flip could be, I'm close, I can smell it or hear it. I have no access to it and I want it. So now my behavior is the complete opposite of pleasure. Okay? So the existence of it near us can do either of them. And so we can see why our body's chemistry can kind of control our behavior. We have to pull our mental strength in order to control those innate behaviors that automatically want to come out, right? That's called maturity. But pain behavior is protective, okay? It's important for our survival. We need to know if something is being injured when we do something, we need to stop doing it. We need to take care of it for survival. So, we will get off of a broken ankle if we're smart. Some of us are a little thicker headed and we just a little bit more, I don't need help, or, you know. So when the brain perceives pain, which is the only place that perceives it, because it gets the information sent by the motor neurons. And so that is because it doesn't want any more damage to happen. When it works and we listen, it's very effective. So we have drugs that can interfere with these getting sent to the brain. That's how pain relievers work. The pain is not non-existent. The message is not getting to the brain. And so there's good and bad results from that. If you're taking strong pain, or people that get like the injections, right? Well, that's good that you're not aware that it hurts, except for now you're going to use the injured area and cause more damage, and you won't know that until that wears off 3 to 6 months later, and now you need to have it cut off or something. When we could have had a little stitch.
Is that epidural?
Well, sometimes. Not during birth. But, you know, yeah, people get steroid injections. Like, well, that's great, except for now you're going right back to work. I have had a student get it, and I was like, okay, well, where was it hurting? Because we still need to act like it's hurting while you're massaging, because let's say it was in the shoulder. I can't move it. Injection. It's fine. No, it's not. It's still deteriorating, and now we're going to deep tissue all day. That's not going to help. And then when it wears off, you have frozen shoulder, and you need big surgery, right? So you have to understand that going into it, and a lot of people don't understand that. Okay, opioids. That is another, there's receptors for those within the nerve pain signal transmitting highway. The body produces some of these. We have enkephalins, endorphins, and that's great. They work really great. When we have those released, we feel great and we're all happy. Floaty after the massage, when we're flooding the brain. It blocks substance P, which is the pain signal that gets sent out. So, when we block that, we're not aware that pain exists. And that's great for chronic pain where no deterioration and injury is happening. It's just a nagging pain. It's not a survival pain at that point. That's fine. So there's a time and place when it's safe to do so. I'm not knocking pain medicine. I'm just saying there's times when it can hurt you, and there's times when it can be helpful. So that will happen also in massage. We will have good hurt, therapeutic pain, we call it in here. That chronically hurts me, right? I have a chronic pain in my hip or sciatica. You're mashing on it, it's creating pain, but I've done this before, and I know when you get done, my chronic pains are going to be gone. So that's why the person will perceive it the time after the initial massage as feeling good. I know it's hurting, but it hurts so good because I know you're getting it out. You're knocking it out. Okay, so that's what we mean when we say therapeutic pain, where it hurts good. We're not causing damage. We're not blocking the artery, right? We're not squeezing on a nerve. We're getting the trigger point out. We're getting the adhesion out so that then the muscle will release and not be painful. And that's what's in that practical application box on 110. Alright, so now we're gonna jump and look at the CNS a little bit closer. Line 11. Brain is the largest, most complex unit of the central nervous system, of the nervous system in general. It has over 100 billion neurons, all nice and neatly packed within our skull. On average, it weighs about 3 pounds, and so it can take up the volume of almost the whole nervous system, about 97%. And most of it is water. About 85% of the brain is water. And we have 4 areas that the brain is divided into. The cerebrum, the diencephalon, the cerebellum, and the brain stem. We will talk about the cerebrum first. That's what it looks like. Okay, so the cerebrum is up here. It's largest section. It's got 2 halves of it. So that's the part you probably think of when you think of brain. It's the cerebrum. So it's called the forebrain. That's cerebrum, aka forebrain. So we have right and left hemispheres, and those hemispheres are connected by what's called the corpus callosum. You do need to know that. So each hemisphere receives information from the opposite side of the body. So left arm pain will be perceived by the right hemisphere of the cerebrum, and vice versa. Whichever hemisphere that we use to speak and write with is what we're called our dominant side. It's our brain dominance is what that means. It doesn't mean muscle dominance, although because we use it first and most, it does have more muscle mass on that side, but it's because the brain is instructing that side to do. And so the pathways are more worn, well worn, and so it can react faster because it has more practice. Switch hands. Write your name. Well, most of you had a pencil. It's going to take a lot more focus for your brain, your muscles in your fingers, because it doesn't do it every day. It takes longer. Now, if you have your dominant side in a sling for 6 months and you have to, that side's going to gradually get faster. So when you practice doing things with your other side, at first it's slow, but it catches on. I do things with my left side, like brushing my teeth and non-essential, non-neat, necessary things, because it's there hanging out all the time. This one needs a break sometimes. Just a thought, because you're going to be working with both sides. Let it get some tone. Okay. Even eating you can try. Not in front of people in a restaurant, but at home, you know. Because the first time you might be distracted and mess your mouth. But after you do it a few days, you're fine. Okay. So, the right hemisphere is associated with, or more, with creativity, imagination, and things of that nature. The left side is more with reading, analytical things, and so that's why people who are more like biochemistry and that, you know, that engineering, they're like, oh, they're more left brain. People who are painting and writing novels. Oh, okay. So we have benefits to both. We need both in the world for balance, right? But it's also the whole cerebrum, of course, both sides. So it's associated with emotions, our memories, figuring out what our response we should take to things. And that's going to be based off of our past experience. How should we respond? If you've dealt with it before, your cerebrum is going to say, well, this is what we did last time. Did it work? Sometimes we have time to figure that out. Sometimes we just respond. And then we go, that's right, I wasn't supposed to do it that way. Bad result again. that is how both sides kind of. Does anybody play a musical instrument or do anything like that? Okay. So that's usually more right brain. Who loves math and science? Okay. Are you ambidextrous? There we go. See what's there. That's great. I like ambidextrous people. I like all people. But that'll be great for using both sides. Hands on. Okay. So, most of the cerebrum is white matter, and it is covered by what's called the cerebral cortex, which is very thin, gray area where you have your dendrites and some other cellular stuff. It just helps with coordination. The cerebrum has 5 lobes. Most of them are named for the bone that's next to it. One is not. We'll learn those in a couple of weeks. But the frontal lobe is our anterior cerebrum area, and that is for concentration like you're doing now, as well as voluntary skeletal muscles. So you use it in the first part of class, and then next week when we start on the table, you're going to use it in the second part of class. So come with your cerebrum ready. All right. 113. The parietal lobe is our next lobe. This one is good for temperature, taste, and pain reception, and other sensory information. The temporal lobe is where we deal with our hearing, our sense of smell. Understanding language is involved in this one, as well as some more complex sensory memory forming from things like smells and music and things of that nature. Our occipital lobe has to do with our vision and things that we see, understanding that, and kind of also body control based off what we see. The insula is part of our limbic system, which is what we feel personally is important or real. So if your child has an imaginary friend, it's real to them. Mm-hmm. So they can get very upset if you sit on them or, because it's real to them. Yeah. Whatever you feel is true. So that's why nightmares are so scary to children, is that it's real. It looks real in their brain, and so they are terrified or extremely happy. So this is part of that area where we are connecting our feelings with our reality. All right, so those are our lobes. Our fear and pleasure and anger is also associated with our limbic system, and we'll talk some more about that later on. All right. The organization of our cerebral cortex. So everything that we have to do comes from sensory information. We receive that, and then we respond, because we've got to get stimulus before a message is sent to cause the action. So our consciousness is how we have our thoughts, our memory, our emotion that's created to ourself in relation to our environment. And we respond to stimuli in our environment based off of a lot of our view of ourselves. If you feel very important and you feel everyone else should feel you are the most important, then your conscious is going to tell you that you are the best at everything and everyone else is below you, and your actions and behavior are going to emulate that. And it doesn't take us long to realize who feels really highly of themselves or who really has a low self-worth of themselves. So we want to try to get closer to a median so people are comfortable around us, and so that we can relate to people a little bit, but not too much. There's good and bad to both sides. We don't want to be run over by all our clients and give away lots and lots of free extra hours that we didn't put on our schedule. That's unbalanced. It's not good self-care. But we also don't want to make them feel small and heavy and not good enough, and that they never tip enough and all these other things. We don't need to make them have low self-esteem either. So there's a balance here. Language. Language is part of written and spoken. Most of this happens in our left hemisphere for 90% of the population. So it's more developed than, countries that are well literate. Our emotions are tied to our limbic system. And mostly we're trying to reach a pleasurable situation. And so that kind of motivates us, whether it's, I hate my car, I want a luxurious car with all the fine stuff. So we're saving and we're working, or I want a different house, living situation. I'm tired of sharing my room or my house with these people that eat my food and leave mess everywhere. So we're motivated from what we perceive as good, pleasurable situations. And so that motivates us, and we're drawn towards what makes us warm and fuzzy versus what's going to make us cold and stressed out. Memories. This involves what we can store, information we store in our brain. Short-term memory is more fragile, and it will go away unless we reinforce it. And sometimes it is not an actual memory, it's information we've been told about ourselves as a child and some pictures and the stories over and over, and then we remember it and we think it's a memory when it's really just a picture that we got told the story about. But if you were never told the story, it would not even be in existence in your brain, right? So to move something from short term to long term where it's more stable and it's going to be able for you to pick it out on your exam later, we have to repeat. That's why learning it in different ways is helpful. Going back over it is helpful. Writing it, hearing it, seeing it, watching it, whatever, all of these things help. Speaking it out loud, that's another one. You can read out loud and say it out loud. Because this makes it more permanent, changing those synapses so that it can send the message to you faster. 10 seconds left. What is it? It's that one. Don't change it. Okay. And if something causes us to have very deep emotions immediately when it happens, it automatically goes into long-term memory, right? Usually our long-term memory starts with a very traumatic experience we had as a child. I know mine did. Like, yep, from then on, I remember everything. Everything else was told to me. All right, learning. Learning is learning how to use these pathways to process information. Advanced learning, like being able to read, is part of the cerebral cortex. The brainstem is just very basic, primitive stuff, like is this hot or cold, because if that's going to burn me or freeze me, I need to not leave my hand there. That's going to be in the brainstem. Very basic functional survival skills. Diencephalon, page 118. One other part that is on the paragraph on 118 above diencephalon. So we talked about habits a little bit last week. We made goals, and changes you were going to make. We have to resist change as human beings. So it takes a lot of effort to start something new or do the opposite and change something, right? That's why changing your eating is hard. Been doing it this way for years. And then you couldn't change for 1 month. Why did everything not stay the same? Because it's not a habit yet. If it's not something you can do long term, it's not going to be a change. It's going to be just a little detour on the side and get back on the highway the same way you've always been going. So, the way that you're learning is either working or not working in here. If it's not working, let's look at what change do I think is going to work better. How can I make that happen? So if you're doing lots of long sessions and that's not working, the information is not there for you to sip off of in the quiz, then we may need to do smaller little bite-sized chunks. Some people's brain is great with a long session. Most people's brain is better with shorter sessions with more repetition. Just pay attention to yourself and what's going on. And if you don't think you've got it, just ask me and I'll help. All right, back to the chapter. Diencephalon. This is between the cerebrum and the midbrain. It has 3 main parts: the thalamus, the hypothalamus, and the pineal gland or body. The thalamus is gray matter, and it is a relay station for all sensory information, except for smell. For all but smell. So temperature, basic touch, reflex, muscles reflexing, and it sends information to the limbic system as well. So it can be part of a natural rhythm flow. Like everyone has a preference for sleeping warm or hot. You know that, your body is aware. So if you're in the opposite situation, your brain is like, we ain't falling asleep. This is not my happy place. You need to take me to a place of pleasure. You need to get some blankets, and turn up some fans, get an ice bath, or take off some layers. Something, right? Once you put it in the situation it knows that it likes, it's going to come. Otherwise you're like, I'm freezing cold, sweating. So just go ahead and do it. And get some more sleep faster. Okay, hypothalamus. So that's your thalamus that we're talking about. She's a very particular lady. Hypothalamus regulates more of our kind of automatic stuff. Our heart rate, our blood pressure, our digestion, feeling full, being happy, feeling good and pleasurable, and coordinating a lot of our sleep cycles and things of that nature. That's the hypothalamus. And then the pineal body, or pineal gland as most of us call it, this is on the back or dorsal side of the diencephalon. And this works with our internal biological clock for all those rhythms we talked about. Seasonal, daily, circadian with the light and dark, revving up, being the most alert, getting ready to go to sleep, being warm, being cold during the day, all of those things. Sexual maturity is also involved, and this does affect the cycle of maturing as our whole organism, does affect our sleep patterns. Through life we sleep more, sleep less, have problems staying asleep. So if you have problems with these hormones not releasing properly, that can have effect on these other related activities from the pineal gland. Brainstem, page 119. This is considered primitive, very primitive part of the brain. There's 3 parts: the midbrain, the pons, and the medulla oblongata. There is a 4th section also that has been studied called the reticular formation or activating system. We usually call it reticular activating system in here. But all of these are based on survival, things you need for basic survival. So, the midbrain, for example, deals with vision, hearing, and muscle tone. The pons help us coordinate our eyes, our breathing, our facial expressions, and therefore it's also in our REM sleep when our eyes are blinking during dreaming. Our medulla oblongata connects the pons to the spinal cord and helps, sorry, scratch that. It helps regulate our blood pressure, heartbeat, and breathing, as well as some simple survival things like coughing and sneezing to expel foreign objects. This can, of course, be fatal if it's not functioning properly, since those are all very necessary for life, breathing, and heartbeat, all of those things. The reticular activating system, the fourth one, this alerts us to changes if we need to be alerted to that sound that we heard outside our window. It can help regulate our heart rate and our breathing patterns to match what we need to be doing. So it helps assist that sympathetic part of the nervous system. All right. And so as it mentions, damage to this system can cause you to go into a coma because you cannot alert the body anymore or arouse the body. And so you see that eye movement is a different system from this movement, and that's why people in a coma can blink, open their eyes sometimes, and it's not actually a response. It's just the different system is not damaged. Gives false hope to the relatives in the room, but that's why. Okay, cerebellum. This is the second largest part of the brain. So cerebrum's first largest, cerebellum is second largest. This has a cortex of gray matter, and the inside is white. Its basic function is balance, coordination of our movements, including giving a massage and balancing and coordinating those movements. So if you don't have good rhythm, maybe your cerebellum is not tuned just perfectly, but it does have a little bit of a connection with the limbic system. They're on the same circuit. So anything that needs coordination, the cerebellum is involved with. The other structures of the brain include the meninges. There's 3 layers of these. They're pictured on 120. These are there to protect the brain and spinal cord. The outermost layer is called the dura. You see the layering there in that picture. It's very tough and fibrous. The middle layer is arachnoid matter, kind of very thin, sticky, cobwebby like. And then the last inner layer is the pia mater, very thin, and it's right next to the brain and or spinal cord. So the outer layer is more durable, it's the dura. The inner layer is, I don't have a word for that one, but it's puny, pia mater. So D-A-P, DAP, is the layering. Okay, so there's a couple different spaces. Do be a little bit familiar with those. Key point would be that the CFS, that cerebral spinal fluid, is within the subarachnoid space between the inner 2 layers, and you have serous fluid to cushion all around between the outside and the middle layer. So you have fluid between all the layers, just a different type. But I think it will help if you remember that the cerebral spinal fluid is around the spinal cord, connects to the brain so that it can talk to all the other nerves in the body, and that stays in the innermost section. So it's there within the space right there in the innermost two layers. Because it's got to go up and surround the brain. Okay, so what is cerebrospinal fluid, or CSF? It is a colorless, watery-like substance. It cushions and protects the spinal cord, and it helps maintain pH balance, so everything is always homeostasis in there, and we want to keep it there. It travels, I think, to like L3, and then up and down to the brain. So it's continually keeping it in contact with all the nerves in the body that way, so that it can always receive information and send it back out quickly. Kind of think of, I guess, since we relate this to electricity, you don't want to be wet in a thunderstorm holding onto a fence, right? Because water conducts electricity faster. So the cerebrospinal fluid helps all these messages happen faster. Ventricles. Ventricles of the brain, they are just 4 chambers that are full of fluid within the brain. And there's a couple openings to the subarachnoid space there, but there's one in each hemisphere of the cerebrum and below, and the attachment to the brainstem. So there's just 4 fluid-filled chambers is basically what you need to know around the brain. The vessels of the brain, just the arteries and things that are coming and connecting to allow blood to be transported in and out around and within the sinus processes, spaces. Spinal cord on 121. Its function is to conduct nerve impulses and integrate the reflexes, the spinal reflexes. It is about 17-18 inches long, and most individuals. It has both white and gray matter of the nervous tissue. It starts at the brainstem, and the exit point of the skull is called the foramen magnum. You might recall foramen means hole in the bone. There are 31 pairs of spinal nerves that connect to the spinal cord. And as they exit the spinal cord, they are then part of the PNS, peripheral nervous system. All right. A couple other key points here on 122. The spinal and lower lumbar nerves together are known as the cauda equina. It just makes that lower section look like a tail, sort of. With a little bend there. So 31 pairs of nerves. You have a pair. So each nerve has an efferent and an afferent nerve. So the sensory information or root is on the dorsal side, and the anterior or ventral root is the motor. Okay, when you're looking at the spine. I guess you can think of it, we know, I think when the dorsal is the back, the dorsal side of the body, the spine, you feel your spinal cord. So, very sensitive here, right? If you're trying to touch the spine here, you just, this is where the act comes out front, the motor off the front. The sensory, you sense it here, it sends the messages everywhere else. That might come. Keep it straight. Okay. The white matter coming down the pathways are called tracts, and these have myelinated nerve fibers. Basically, a tract is a collection of all the nerve fibers that have one common function. It's just they're going to do the same thing. So the collection of them is called a tract, a nerve tract. So the ascending tracts all carry that sensory information towards the CNS. The descending coming down from the brain going out to the body, descending, and it's carrying motor information, a message of what you want the body to do. All right, so last page on 123. The sensory ascending tracts. The first one is called primary, and it is from the receptor to the brainstem, direct connection. And we're going to talk more about all the PNS stuff in the next chapter, so this is more focused on the CNS. Where you cross over the sensory information across over sides, that has to reach a secondary neuron before that information goes to the thalamus, where it gets processed. And a third neuron goes to the parietal lobe of your cerebral cortex. This is called the internal capsule. So you've got three little branches coming out. Primary, think of brainstem, very primal functions for life. Secondary, or the second one goes to your secondary neuron before it goes to the thalamus to be translated. And then the third one is going to the parietal lobe. Alright, descending. Descending goes from the CNS towards the muscles with the message of what to do. So this has to do with moving our body, how we hold our posture, as well as writing on the paper. Those little fine motor skills, or building something with your little fingers. They come out through the lateral corticospinal tract and out to the skeletal muscles using the motor neurons. There's upper and lower motor neurons. If you get injury to the upper, you will have more rigid movements, exaggerated responses to simple reflexes, instead of like a little kick when your knee gets, knock the doctor out of your head. It's hyperactive. This is called spastic paralysis, when the upper motor neurons are damaged. If it's lower motor neurons get damaged, then you're missing signal. It's not getting sent properly. This is called flaccid paralysis, lack of movement. Flaccid, make you think of lazy, don't want to move. Spastic, can't get the person to calm down. So hyper, upper, flaccid, lazy, lower. And that's it. It's a lot. I know. That's all we only have two really sections this week. Alright. So let's take a brief break before we switch to massage information. We don't cover the pathology sections in essentials because we're going to do pathology as a separate